Okay, good afternoon, all. So this video is going to be an extra supplementary material to our regular videos on AM2200 strength of materials. A lot of you have asked questions regarding the notation of stresses, whether they're positive or negative, which direction they're positive, which direction they're negative. So this video is to supplement those discussions that what directions we consider as positive and what directions we consider as negative. Okay, so this is on sign convention that we have on stresses. All right, I am not going to use any of these books, but point is these books are what I refer for these lectures, and today it's not going to be anything from the book, so it's going to be completely my own lecture for you for discussions. Okay, let's first look into a three-dimensional object. First, a three-dimensional object. So let's say I have a coordinate system, a right-handed Cartesian coordinate system. This is x, this is y, and this is z. And let's say there is a body. Okay, there is a body, and the body is undergoing few kind of stresses, some distributed stress, forces, some normal force or concentrated force, let's say P1, W1, P2, like this. A lot of forces are acting on the body, P3. Now, you as a designer is interested on a particular point in the body. You are actually interested in all the points in the body, but you cannot solve all the points at a time, so you have to solve one point, and then probably we can find out functions that will uh, combine or that will form a relationship between all these points. So let's take only one point. Let that point be defined as Q point. Okay, and as I said that this is a deformable body, so this is a deformable body, by which I mean the relative distance, the relative distance between two points, any two points, no, between any two points, is not same before and after loading. Okay, that means if I consider 2 points in a body, let me uh, explain it with a picture here. Let's say I have a body, a cantilever beam sort of thing, or a bar, whatever you want to consider. Okay, and you have put a load here P. So before loading, let's say before loading, the points were these two, A and B. Okay, and they had a distance like this, which was the relative distance between point A and B. Now after deformation, after you put the load, they will either compress or elongate. In this case it looks like they have compressed, so I will just change the direction of the load so that it looks like they have compressed. Okay, let's say the point load acts in the opposite direction, so like a compression on the body. So the point A and B will have a reduced distance now. So this is A, this is B, so the points got reduced by certain amount. Okay, so in a rigid body, under rigid body motion, the body points, any two points in the body doesn't uh, change with respect to each other. Okay, they change only in the sense they rotate, they can rotate about each other, but there won't be any deformation or any relative distance that changes between them. Okay, but in case of a deformable body, if I take 2 points, the relative distance between them will change. That means there will be, if you have a measure of the distance between them, that distance will change. But in a rigid body, the distance will not change. It can rotate, the point can rotate about one point and the other, okay, but not have any deformation. Okay, so I was discussing about this. So now let's take a section on this body. Let's say that I take a section which is passing through this point Q and in this direction. Okay, so if you now look at the body will look something like this. Right, with the point Q somewhere here, and the body will have maybe some, this is a three-dimensional body, so some section will be there on other direction. So let's say this is the point Q here, and I get a section. Now what you do, you consider a cuboid around this point Q. The cuboids are taken such that the sections that cut the cuboids are parallel to this x, y, z axis, are parallel to your considered x, y and z axis. So what I will do, I will assume a cutout of a section that goes like this, and if I do that, I will have something like this, right, which will look like, and the point Q here. Okay, now you do another cutout, another section cutout which is parallel to your xz plane like this. So now your section will look like something like this. Okay, it will look something like this, and then you assume another cutout that may not be possible to see in this page, but you take another cutout which is along xz plane like this. Okay, so you take one like this, another on the back side like that, so you get two more face which will, okay, let me first rub this Q out of this place, which will make a cuboid kind of design here. Very good, very nice. So this is the design element, or this is the very small element, volume element that I have considered around the point Q. Note that this volume element should be very small as possible. Okay, very small, and you have to consider it around the point Q. The distances or the sizes of this thing need not be same, so we can name it as dx, we can name this guy as dz, and this guy as dy. Okay, so the volume is del V equal to dx dy dz. All right, that's the volume of the element. Now my point is, I need to find stress around that point Q, right? So I am trying to find stress at that point Q, but I am considering a volumetric element around that point Q. So therefore I have how many faces? I have 6 faces around it. So one face, two face, there is third, there is fourth, and this is the front is 6, and the back side is 7, right? So I have 1 here, 2 here, 3 here, 4 on this side, 5 is this front face, and the back side there will be another one, that is 6th face, right? So let me so I have just increased the video size so that it's possible to view what I am planning to say. So this is, let's say, a body, a three-dimensional body in a three-dimensional place. Okay, three-dimensional object. So with these walls of this room can form a three-dimensional axis, and this is a body. Okay, so you are considering a small point somewhere here on the body. Let's say you want to find somewhere inside there is a point Q where you want to find the stresses around it. Okay, so what you do is you assume a very small element around that point Q, very small, very small as possible. Let's say like this. So that might look like this in terms of this whole building. Okay, so this, you assume this to be a small element. Okay, now this small element, when I blow it, it will look like a cuboid like this, right? Okay, this is clear. So that's your, so this side is your del x, this is your del y, and this one that is going out of your video plane is del z, right? First thing is the normal stresses. All normal stresses that are outside this body, that is going out of this body, are positive. Like going out of this body are all positive. Let me show you with a proper arrow, if I have one of them. Yes, I got the arrows. So anything that is going out of this body as a normal stress are positive. So this is its positive direction here. Okay. Similarly, I can assume another one. This is its positive direction here going out, and this one is also positive direction here going out. So all these three are positive faces of normal. Okay, these are all positive. If you have this body like this, so this all makes it positive, all these directions. So let me hold it like this, then it is properly visible, I think. So all these are positive. Similarly, on these are the positive x-axis directions. This is positive y-axis, and the opposite side is positive z-axis like this. So if you have another one on this direction, this is also going out of the body, so that's also positive. This is also going out of the body, that's also positive. This is going out of the body, that's also positive, as well as one that is here towards me going out of the body is also positive. Okay, so I will not show it by a diagram. So all these forces, so this is positive normal stress, this is positive normal stress, this direction there will be a positive normal stress here, this direction there will be a positive normal stress, there is a positive normal stress in this direction, and there will be one on the other side of the face, so outside, right, that direction. All these are positive normal stresses. Okay, and all these normal stresses act in the positive directions of x, y, and z, as well as in the negative direction of x, y, z, but on the negative face. Okay, so I will draw a few things here to show you. One is, this is a positive x face. Okay, this is positive y face, and this is your positive z face. So if you have a cube, or you can see it yourself, you have a cube. Okay, so this is my positive x face, and this is my positive y face, and that's my positive z face. And any normals that are along the positive x-axis are positive, so we'll name it as sigma xx here. This is at sigma zz here, and this is sigma yy here. Okay, what about the opposite faces? What about the faces that are opposite to this? Those faces are negative faces, right? But the forces or the stresses are also acting towards the negative x-axis. So this force, if you consider this stress is acting on a face that is negative x face, right? This face is a negative x face, because it's if this is a positive x face, this is the opposite x face, so that's a negative x face. So that negative x face and the force that is acting on negative direction makes it a positive force. So this becomes again positive sigma xx. Similarly, I can find that this bottom face is the negative x y face, right? This is a negative y face, and this negative y face, and the force acting is a negative direction here. So that makes this sigma yy as positive. Similarly, this will be sigma zz, which will be positive, because the phase that is acting here is a negative phase. So this is a negative phase of z axis. Okay, then that's is. So in a nutshell, if you want to tell me what are these things, I will tell like this. So if you have a body, three-dimensional body like this, and you chose a point Q here, around which you have taken a volumetric element which are given by dx, dy, and dz. Okay, so the positive normal stresses acting on the body will be along this direction, sigma xx, sigma yy, sigma zz. These are my x, y and z positive axis, right? Similarly, the force that is going here is positive sigma xx. The force that is going out of this plane, that side, something that is going out here, sigma zz, and something that is going down here is sigma yy. All these are positive normal stresses. They act as they are coming out of the element. One more point, why they are considered to be positive? They are considered to be positive because they provide normal stress, sorry, because they provide tensile stress to the element. Okay, I'll stop here.